All righty, folks. Good to see you guys again. Probably you're on your Thanksgiving break at this point in time. So let's see if we can't talk a little bit about vectors. So we're going to do vectors in one day. We're just going to get a taste of it just so we have a general idea of what's going on. It's something you will use especially in physics. Basically, a vector is anything that has magnitude and direction. So in other words, it's a force going in a particular direction. All right, that magnitude essentially is going to end up being some magnitude is really the hypotenuse of some sort of right triangle. So we're going to use a lot of Pythagorean theorem. And the direction is the angle of this right triangle as well. So we'll use tangent a lot as well. So really we're going to be doing a lot with the Pythagorean theorem and tangent. So magnitude and direction. So what we're going to look at first is how do we put something in component form, and then we'll play around with it just a little bit more. So component form, for whatever reason, we have it down here a little bit. So it's a little bit right here, terminal minus initial. To find the component form of a vector, what we end up doing is we want to go ahead and figure out what it is where we take the terminal or the endpoint and subtract it from the first point. So let's see what we got here. First up, we have some vector u that's going to be at 0, 0, and it's going to go to 5, 8. So if I were to draw that vector u, let me see if I can draw it real quick. Starting at 0, 0, and I'm going to 5, 8. So it ends at a point. Now this point, you can see that it ends or terminates there at 5, 8, and it begins or starts at the point 0, 0. So whenever you're dealing with any sort of trying to turn it into what we call a component form, you take the foot and you take the head and you subtract the foot from it, or the terminal point. You take the terminal point and you subtract the initial point, which you see down below there, but I just want to write it up here. So we have a terminal x and a terminal y, an initial x and an initial y. So if they're the same vector, then they should have the same component form. So technically, you either bold it like you see it down here, or if you're writing it in general, you use u with kind of a half arrow. Now, components are going to be not a parentheses, but this weird little caret thing. So I'm going to take my ending x, 5, and I'm going to subtract my first x from it, 0. My ending y value, which is 8, and subtract my initial y value, which is 0. So that means my component form to u would be 5, 8. Now v is the same direction and magnitude. If they're equivalent vectors, that means it's going to have the same component form. So why don't you guys go ahead and take a second and see if you can graph the component form for v. All right, so let me see if I can try this here. I'm going to start at 311, and that'd be somewhere over here. And I'm going to end up at 0 or 819. So here's my ending point. Here's my beginning point. So we have 311. That's my initial point, and it terminates. So my terminal point is 819. So I'm going to write it in its component form. So vector v is going to be the initial x, the terminal x, 8, minus the initial x, 3. The terminal y, 19, minus the initial y, 11. If they are equivalent vectors, they will have the same component form. You notice it's still 5 and 8. they have the same component form. So they both have a change in x of 5, and they both have a change in y of 8. Therefore, they would have the same direction and the same magnitude. So let's take this point down here, this vector v, using this idea. So we now have some vector, oopsies. We have a vector, a different vectors at 6, -5. So let's take a look at where that would be, 6, -5. And we'll draw this vector. Roger, what's your vector, Victor? Well, I've got Clarence. Every time I get to vectors, I always think back to that line in Airplane. So 6, -5. That means it's going to start at 0, 0, since it's in component form, and it's going to end at the point 6, -5. So it'll be right about here. So there's vector v. If I want to find the magnitude of vector v, that's basically doing the Pythagorean theorem. So I'm going to take x squared plus y squared. If I want to find the direction angle of any vector, that's going to be the initial. I'm going to start with tangent of y over x. And I'm going to have to do a little bit more to it because I got to put it between 0 and 360 degrees, or 0 and 2 pi. But the theta that goes with that angle will be inverse tangent of y over x. So our component vector, if I come back here to my component, I have a y value of -5. I have an x value of 6. So I can find my magnitude of this vector. In other words, how strong is this vector? How forceful is this vector? By doing the Pythagorean theorem. So 6 squared plus -5 squared. Some people call a vector a directional force. We have 36 plus 25. That means the magnitude is root 61. In other words, it's root 61 units long. Now, when I do my theta, I know that this is going to be giving me an arctangent value. So I know it's going to be a negative value they're going to give me because it's down here in quadrant 4. So we have -5. So my angle that they're going to give me would be, when I plug this into my calculator, I end up with -39.805 571. Now I can't state this enough, friends. When you're dealing with these, always graph out your vector, so you have an idea where it is on your 4 quadrants, where it is on that unit circle, because you're going to need to know that, because you might have to do some reasoning. It's not always going to be just the angle value. Matter of fact, a lot of times it's not just theta. So I'm looking at this thing and I'm going, all right, well, I could leave that as a negative value, but if I want to put it in terms of 0 to 360, then I'd want to go ahead and think, let's do a coterminal angle to it to see if I can't figure out what that would be from 0 to 360. So I could say my direction would be at -39 degrees, or if I wanted to, I could also say that it would be from the at 320 degrees, 0.1944. And technically, I guess I should be using squiggles, not equal signs. So direction is always going to be some angle, inverse tangent of y over x. And magnitude is basically the Pythagorean theorem, the square root of x squared plus y squared. So we're going to play with these ideas today. We're not going to do anything too terribly overly more complicated than this, but we're just going to play with these ideas, and we're just going to throw some random problems out there and see if we can play with this and get a little clearer picture of how this all works out. So let's try this one. Given v equals -8/3, find the magnitude of v. So why don't you guys go ahead and start off there. Just do the first part, and then we'll deal with the rest of it later. All right, so magnitude of v. So the magnitude of v, that's just going to be the Pythagorean theorem. So -8 squared plus 3 squared. And that would be the square root of 73. So that means this vector is root 73 units long, or has a magnitude of root 73. A unit vector is a vector that is 1 unit long. So if I wanted to figure out how to make this 1 unit long, it's actually not too bad. All you got to do to make a unit vector is you take whatever the components are, and you're going to divide it by the magnitude of whatever vector you were currently looking at. So for me, the unit vector, which they said is u, that's going to be whatever my components are of my original vector, -8, 3. And I'm going to divide it by its magnitude. So that would be a 1 unit vector. A unit vector is 1 unit long. Well, how can we guarantee that that actually is a 1 unit vector? Easiest way? Do the Pythagorean theorem of it. Figure out its magnitude. Was it actually 1 unit long? I want you guys to be able to kind of wrap your brains around it, so that way you feel good about what's being actually done here. So I want to find out and guarantee that it's 1 unit long. I can just plug it into my magnitude formula, essentially the Pythagorean theorem, and I could figure it out. So the magnitude of u, was it actually 1 unit long? We got 64 over 73 plus 9 over 73, which is 73 over 73. And it turns out, friends, it really is 1 unit long. So if we want a magnitude that's not equal to 1, you just take that magnitude that you want and multiply it by the components of the unit vector. So for instance, let's take the problem 3. It says find the vector in the same direction. I don't know why that says 4. That should be problem 3, or it should be u. That is 10 units long. So if I want a vector that is 10 units long, so I'm going to take whatever u is. So my unit vector. If I want it to be 10 units long, so I now know that this is 1 unit long. I want to find a vector that is the same value, but 10 units long. So in other words, I'm going to take that unit vector and I'm going to do a scalar multiplication. I'm going to multiply it by 10. So I'm going to multiply this by 10. And when I do that, friends, I end up getting a unit vector That is now a 10 unit vector. So negative 8 times 10 would be negative 80. And 3 times 10 would be 30. It is now gone from a unit vector to a 10 unit vector. And this doesn't mean a whole heck of a lot right here. All this basically says is, hey, we can add the components of two vectors. You can subtract the components of two vectors. You can do a scalar multiplication of two vectors. This last little bit is kind of an interesting idea. It's something called a linear combination. Sometimes we don't like to write it as a vector. Sometimes we like to write it in this linear combination. And notice, the linear combination is really a combination of what they call unit vectors. So how is negative 11, 7 the same thing as negative 11i plus 7j? Well, let's talk briefly about that, because I think we can do that real quick and we can kind of see it. If I were to take this component vector, I could break it out as negative 11 comma 0 plus 0 comma 7. I can break it up because, again, vectors can be added. And I can simplify, or I can factor out the negative 11 because vectors can have scalar multiplication. So now that I have a negative 11 plus 7, notice the vector I is the unit vector 1, 0. Notice I in this case is not the square root of negative 1. I is the unit vector. So negative 11i plus the j unit vector, which is 0, 1, j. So it'd be negative 11i plus 7j. Those say the same thing. We have one that's in component form and one that is called a linear combination. It's a combination of unit vectors. So we're going to play with this idea a little bit now. And like I said, we're just going to be doing some different things here. I want to add one more little bit to this as well. Let's let D be write U as a linear combination. All righty, friends. Why don't you give that a shot there, see what you come up with, and then we will talk about it. Go ahead and pause the video and try each of those. All right, well, A I think isn't too bad. So A just says negative U. So in other words, we're going to take negative 1 and we're going to multiply it by U. So we end up with negative 3 and 5. All right, why don't you guys try the next one? Negative 2u minus 7v. Go and pause that one, see what you come up with. All right, so negative 2 times 3 negative 5. And we have negative 7 times v, which is negative 8, 2. So negative 6, 10 plus 56, negative 14. And all together, that ends up being 50 -4. All right. Our next one we have 3 times u plus 4 times v. Why don't you guys go and pause the video here and see if you guys can't take a little shot at this one. All righty, we got 3u plus 12v so 3 times 3 -5 plus 12 times -8 2 and we have 9 -15 plus -96 and 24, which is equal to -85. Oopsies, -87. I should probably change that there. There we go. And 9. All righty. And the last one, the linear combination. So this is u I can write it as 3i plus, oops, plus, let's make that a negative, minus 5j. Linear combinations. All righty. We're able to just add and subtract our vectors to basically combine them. All right, let's keep going here. We'll play a little more here. And again, more stuff dealing with terminal points and initial points, and more of the standard unit vectors. All right, so why don't you guys pause the video, try number 5, and see what you come up with. All right, so the first thing we're going to have to do here. We're going to have to write u as a vector. So remember, it's always going to be terminal minus initial. So it's ending at 4, start at -5. It's ending at -1, but it started at 9. So we end up with 9 and -10. Next part says write u in component form. I can do that. So that would be 9i minus 10j. All right, why don't you guys go and pause the video? Let's see how you guys do on number 6. Go for it. All right, so first thing I got to do is find a unit vector u in the same direction as v. All right, so u, I lied. I better first figure out the magnitude of v. So we have 8 squared plus -6 squared. So we have 64 plus 36. And that's going to be equal to the square root of 100, which is equal to 10. So that means the unit vector is going to be whatever the components are of v divided by its magnitude. So 8/10 and -6/10, which is 4/5 and -3/5. Last thing, find a 5-unit vector W in terms of V. All right, so W is going to be 5 times whatever U was. So 4/5 and -3/5. So that means it's going to be 4, -3. All right, friends, why don't you guys pause it one more time and see if you guys can't figure out problem number 7. Here we go. All right, so first thing I need to do, I probably want to go ahead and take U out of the component form, or out of the linear combination and write it in component form. So that's going to be -4, 7. So V was 9I minus J. So that means V would be 9 and -1. So 1/3 U minus 5V, that'll be 1/3 times -4/7. Minus 5 times 9 -1. And we end up with -4/3 and 7/3 plus -45 plus 5. Or positive 5. I mean, I guess we could say plus 5, but probably not appropriate. And when we add them together, friends, we end up with -46 1/3 and 7 1/3. Which is the same thing as, if you wanted to do the linear combination for it, you could do that as well. So -46 1/3 I plus 7 1/3 J. So the only thing we really haven't played with yet is this idea of the directional angle. So we played a little bit with it, but we're going to go and do a little bit more with it. And again, remember what the directional angle is. It's that tangent. The directional angle is that tangent of X and Y. So in other words, and again, it could be anywhere on here. So I could have any vector I wanted to, whatever this component vector is. That directional angle is always going to be the inverse tangent of y over x. But we sometimes have to play with it a little bit to make sure that it's on our unit circle. So let's take a look at this first one here. I have, find the directional angle of 711. Okay. So here we go. We have 711. And again, just to show why it's tangent, I'm going to go ahead and draw out the components here. So the x component is 7, the y component is 11. So tangent of theta then is 7 or 11 over 7. I just realized when I did this earlier, I did it backwards. I did 7/11. I'll have to fix this. All right, so the inverse tangent of 11 divided by 7, which would be, oh, let's see here, second tangent, 11 divided by 7. Be about 57.5288 degrees. So that means my directional angle is approximately 57.5288 degrees. All right, well, let's try. Why don't you guys go ahead and pause it and try number 9 yourselves and see what you guys come up with. Go for it. All right, let's see how you did. So -8/16. So let's first draw where that would be. -8/16 be down here. So -8, -16. But you need to remember what happens with when I do my inverse tangent. My calculator will think of it as arc tangent. So it's only going to give me an angle from -pi/2 to +pi/2. Or it's going to only give me an angle from -90 degrees to +90 degrees. Well, that's not going to work here because, friends, I'm in quadrant 3. So when I get done finding my theta, just realize I'm not quite done yet. I have to do a little bit of work to make sure that my angle fell in quadrant 3. So tangent of theta is 2. So I'm looking for the inverse tangent of 2. So theta is approximately 63.4349 degrees. Let's think here for a second. Friends, that would be up here. I still got to figure out how to get all the way down there. So I got to remember that the period for tangent on the graph is pi, or 180 degrees. So I have to go 180 degrees more to get my directional angle. So my directional angle is going to be 180 degrees more than that. So theta plus 180 degrees, which would be about 243.4349 degrees. So that means the directional angle is approximately 243.4349 degrees. And I just realized something here. I apparently wanted there to be more than one angle. Not really sure why. There we go. Oops. There we go. All righty, friends. So that's just a little introductory cursory look at vectors. We're not going to go that much more than that this time. This last trig unit, we're just going to be introduced to a bunch of different little places where trig is involved, and use it in various ideas. So anyways, I will hopefully you guys have a wonderful break, and I can't wait to see you when you guys come back from Thanksgiving break. All right, talk to you guys later. Take care.